This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hi, this is Priyanka Raghavan for Software Engineering Radio. Today, we'll be exploring the topic, how to build an LLM-based application, diving into the right use cases, architectural choices, and how to select the right models for your needs. My guest today is Srujana Merugu, a seasoned researcher having worked with research labs at Yahoo, IBM, Google, and Amazon with more than 2 decades of experience tackling large-scale data science challenges across enterprises, e-commerce, and government collaborations. Srujana holds a PhD in computer science from the University of Texas at Austin and a bachelor's in electrical engineering from the Indian Institute of Technology, Madras. Welcome to the show, Srujana.
Hey Priyanka, great to be here with you, and thanks so much for having me on your show. Pretty excited about this discussion and I'm looking forward to it.
Though we have done many shows on large language models, such as episode 582, Programming with LLMs, episode 533 on GitHub Copilot, episode 673 on RAG, and recently episode 693 on AI-assisted debugging. It would still be beneficial for our listeners if you could define a few terms before we move deeper into the show. The first one I wanted to ask is, what is the difference between generative AI versus deep learning versus predictive AI?
Yeah, this is a great place to start. So, before we get into the deeper nuances of generative AI, I really think we should clear up some of the vocabulary that gets tossed around. So, let's imagine a Venn diagram with nested circles. So, the largest circle here would be AI that encompasses all kinds of intelligence that do not have a natural origin. Historically, these used to include even rule-based expert systems and smart search algorithms like the ones used in earlier versions of the Stockfish chess engine. However, the most important AI methods are the ones based on machine learning, where we learn patterns from data. So ML is sort of nested inside AI, though nowadays they've become nearly synonymous. Now, within machine learning, the current dominant subclass of algorithms are deep learning methods. And these are methods based on multi-layered neural networks. And these include models such as RNNs, recurrent neural networks, and CNNs, convolutional neural networks. And also the most recent crop of generative AI models. Now, the generative AI models are the ones that ingest inputs and they generate artifacts of complex modalities like text, speech, images, video, and so on. And the ones that focus on language in particular, for instance, the original GPT models, are called generative LLMs, where LLM stands for large language models. So essentially, we have these concentric circles of AI, then ML, then deep learning, then generative AI, and within that, generative LLM. Now, Priyanka, you also asked me about predictive AI. This is sometimes referred to as discriminative AI, and these are models that output numeric scores or vectors or categorical labels. Unlike the generative AI models that output complex artifacts like text and images. Most of the ML work till recent years used to focus on predictive and discriminative models, and that span different model classes like decision trees, kernel machines, linear models, and neural networks. Now, from an application point of view, classification of an email as spam or not would be something powered by predictive or discriminative methods, while generating that email would require generative AI. So I hope that clears it up.
I think it does. And we can move on to the next terms I want you to define for me, which is, what is the pre-trained model versus when someone says you need to fine-tune a model?
Right, yeah. So to understand these terms, pre-training and fine-tuning, let's take a step back and look at how generative models are trained. Now, this process is a little different from the traditional supervised learning paradigm, where we train models on labeled examples like emails marked as spam or not. And traditionally, this learning used to be for a specific task. Generative models, on the other hand, go through a multi stage training process that closely mimics how humans learn and specialize. So, here, the first stage, which is pre training, essentially gives the model broad education about the world. The model learns from massive amounts of unlabeled data. That is, we don't have any labels, and these could be books, Wikipedia, public web, and so on. And this is done without any specific target task. So, in this phase, the model learns broad patterns and reasoning structures, just like how people learn foundational knowledge in school. For instance, a language model might learn grammar, idioms, and context, and a vision model would learn about spatial coherence and patterns like humans having 5 fingers and not six. And the result is a powerful foundation model which understands this broad domain of text or images, and it understands it deeply enough to generate realistic continuations. So think of this as some sort of powerful autocomplete. Now, once we are done with this pre training stage, the next stage is the supervised fine tuning stage. And this is similar to vocational training of humans for specific professions. So, here what we do is tweak the model parameters for a particular task or set of tasks using label data, right? Now, LLM providers like Google or OpenAI already do some fine tuning for very common tasks like, say, summarization, question answering, and so on. But in some cases, organizations might want to fine tune pre trained models on their proprietary data to further enhance the performance. So they use a variety of methods, and these span a large spectrum from updating all of the model parameters to adjusting just a few using lightweight techniques like LoRa, which is low rank adaptation. Now, I want to mention that in addition to pre training and fine tuning that you asked about, Priyanka, there's actually an important third stage, which is alignment. So, this is about guiding the model's behavior to ensure that the responses are helpful, safe, and aligned with human expectations. So, this stage is a bit like giving people performance feedback after they are on the job. So the model is already generating responses and then we are flagging it as good or not. And this step uses techniques like reinforcement learning from human feedback, that's called RLHF. And now there are more recent techniques like PPO, proximal policy optimization, DPO, which stands for direct preference optimization. So let's not bother about the various techniques, but the whole idea here is that the models are now trained to prefer responses that are better suited for human preferences. Now, outside the ML community, folks have been using fine tuning to refer to any form of customization, whether that's supervised fine tuning or alignment or even prompting it, right? So that kind of works informally, but in technical settings, it's better to use fine tuning to refer to the supervised fine tuning step.
It would make sense to move on to the next question, which is also important, which is the term transformers, which is used in GPTs. What does that do?
Right, right. See, the T in GPT actually stands for the transformer architecture, and that is the core model architecture powering today's LLMs. So, this was first proposed in 2017 in the famous Attention is All You Need paper, and it's designed around the idea of attention, which is essentially a mechanism that lets the model focus on the most relevant parts of the input when it's trying to either create an embedding or generate predictions. So, typically in language models, we encode input sentences as sequences of tokens. Tokens are essentially parts of words, and you can think of these tokens as atomic units of the model's language. Now, in earlier language models like RNNs, we used to process this input data step by step in a sequential manner. But in transformers, we handle all tokens in parallel, and that makes it highly flexible and scalable. In fact, this was the innovation that made it feasible for us to build these massive models with billions of parameters. Now, to go a little deeper in the transformer architecture, we have two main components. One is the encoder and the other is the decoder. Now, the encoder takes the input, our sequence of tokens, and it processes it through layers of self attention. That is, each token gets to look at all the other tokens, and this enables the model to understand relationships between all parts of the input. And as a result, we get a set of very rich contextual embeddings. Embeddings are nothing other than just vectors, right? So we have representations for each of the token in the form of a numeric vector, and that encodes the meaning of the sentence. So essentially, we are translating the input text to a vector. Now, the decoder takes these embedding representations or vectors and again uses the attention mechanism to generate output text one token at a time. Now, some of the earlier models that were around, like Google's T5, had both encoder and decoder. Most of the current generative LLMs like GPT only use the decoder, and it's optimized for text generation. And of course, we also have models like BERT, which only use the encoder because it's targeted towards understanding the text, doesn't have generative responsibilities. And now we've gone beyond text to other modalities, and some of these ideas are being used there as well.
Yeah. So, based on what you just said, where we go beyond the text and we use multimodal, which is both images and videos or anything else, could you talk to us about two other terms, which is diffusion model versus vision transformers?
Oh, yeah, yeah. I mean, I'm glad you brought this up because now we've made a lot of progress on vision models, and most of the Gen A tools that we use, like ChatGPT, actually support both vision and language, and in fact, audio too. So, while folks were exploring language focused generative models, there was also this big parallel effort on image generation. And this separate evolution came about because of a fundamental difference between language and image modalities. So, if you think about it, language is discrete and sequential. So, words come in a fixed order and that results in a distinct meaning. And so, predicting the next token made a lot of sense. Images, on the other hand, are continuous and spatial, and the meaning emerges from patterns across pixels rather than their order. So, transformer architectures, which excelled at handling dependencies across a sequence of tokens, were a natural fit for a language. But for image models, we needed architectures that could deal with noise and spatial coherence. So, it turned out that diffusion models, which were first studied in physics, were a good fit. So, these diffusion models learn to create images using a simple but powerful idea. And the idea is something like this: you take real pictures, gradually add random noise until the picture becomes completely unrecognizable, and then we train the model to reverse this process via what we call iterative denoising. So, essentially, we recover the original image by removing one step at a time, one iteration at a time. Once we train this model over millions of images, it learns visual patterns that make an image look real, like the edges, the lighting, perspective, texture, and all that. Once we have a trained model, we run this model in reverse. So we start from random noise and then we do this iterative denoising one step at a time until we have a coherent image. Now, given some input text instructions or a reference image, if we want to generate an image, we first encode those inputs as vectors, and those vectors steer this image generation. So you can think of diffusion models as digital artists who are splattering paint all around and then they're sculpting some order out of chaos. So, in essence, the model turns that random spray of paint into realistic images, one brush stroke at a time. And most of the earlier versions of DALI and Stable Diffusion were these pure diffusion models. So that's about the diffusion models. Now, while diffusion models were perfecting this image generation, we also had big advances in the field of image understanding. And that was done through vision transformers or VITs, the second class of models that you asked about. So, the core innovation in VITs is that we treat an image exactly like a sentence. So, we break the image into a sequence of small patches or visual tokens, and then we feed it into a standard transformer architecture, the one that we talked about a little while ago. Now, this allows the model to learn not only local but long range dependencies across all the tokens of the image. This was not possible with the earlier generation of vision models, which were like focused only on the local dependencies. So, VITs proved that the power of attention mechanism, which really transformed language understanding, could be equally transformative for vision, and soon it became the most dominant choice for visual understanding. Now, given that we have these tools for generation and understanding, the obvious next step was to merge these two, and that led to diffusion transformers. So we had diffusion and we have transformers. It's called DITs. And these models essentially take the VIT architecture and use that to replace the traditional backbone used in denoising in the diffusion model. So we kind of like merge these two. And this fusion is really the bedrock of our modern, highly scalable and realistic video generation systems like OpenAI Sora. So we have now all of these cool models, and we have both the vision and language merged in unified models as well, because we have transformers and diffusion models combined.
Wow, this is fascinating. And it would make sense to go to the next part now that we've got the definitions out of the way. We have discussed use cases in other episodes which we did on large language models, but it was mainly to do with code generation and debugging and programming. But this area is also transforming areas like video creation, like you just alluded to, text editing, and even medical sciences. From your experience, what are common use cases where Gen AI is used?
Yeah, and it's really true that there's so many use cases right now, and it's pretty remarkable how things are shaping up. And it's really become a very versatile engine that's reshaping a lot of domains. And if you look at the landscape today, I would group the most impactful Gen AI use cases into four main buckets. The first one is really where it started for most of us, and that is chatbots or software knowledge copilots like ChatGPT, Gemini, Claude. And these are systems designed to augment human intelligence and productivity. What makes them so powerful is their dual capability. On one hand, these copilots interact with humans in our natural modalities like text, audio, images, or even video. And on the other hand, they can also talk to automated tools through API calls. So, this bridging capability is a game changer. On top of that, the underlying models also come with world knowledge. They're getting progressively better at reasoning, planning, and they can tap into internet resources when needed. As we all know, for the software engineering community, this shift has been transformative given how quickly people have adopted all of these code centric Gen AI tools like GitHub Copilot and Cursor AI. Most of you, I'm sure, are already using these tools for code refactoring, debugging, for unit tests, design documents, and so on. It's the same story in all knowledge intensive domains, so you don't have to go into details there. In fact, I would say that for most knowledge workers, tools like Microsoft's Copilot have become the ultimate personal assistants because they
Mm.
handle everything from meeting summaries, email drafts, and even creating complex reports. So that's the first big bucket. Now, the second class of use cases revolves around process automation and agentic systems. Now, unlike co-pilots where we still have a human in the loop, these are autonomous agents and they can plan and execute multi-step tasks on their own. So typically these agents would handle workflows that would normally be assigned to a human. Something like auditing suspicious e-commerce transactions, planning travel, doing some analysis of stocks. And increasingly, we are seeing customized task specific agents being built for various domains on top of frameworks like OpenAI's Assistant API, AutoGPT, and Crew AI. Now, apart from these first two buckets, there is a very important third bucket that most of us seem to be encountering, which is multimodal content design and creation. And this is the creative frontier of Gen AI. As we just now discussed, we have these powerful diffusion transformer and neural radiance based models. And these include the latest versions of DALI, VO, and Dream Fusion. Dream Fusion is the one for generating 3D scenes. And these models can generate highly realistic output images, video, 3D models from text or even other reference input. And they can do this with high fidelity and coherent style. And the same is now true for audio models, which can be used to generate music, human speech, and even environmental sounds. And as a result of all of this, we are seeing a dramatic overhauling of content creation workflows across advertising, across filmmaking, game design, architecture design, and a lot of other domains. Now, apart from these three buckets that we might have encountered in our everyday lives, there is an important fourth bucket, which is actually the most profound one, and that is scientific discovery. If you saw last year's Nobel Prize awards, you would definitely relate to this. So, here, Gen AI is acting as an instrument of science in various application domains. And one important use case is custom models to generate new structured artifacts. For instance, models like AlphaFold 3 are helping design entirely new protein structures and molecules, which is accelerating drug discovery in ways that used to be unthinkable a few years ago. Apart from this, another critical work stream is generation of synthetic data sets that mimic real data. And that's particularly important for high stakes domains like healthcare and finance, where privacy and safety are very important. So, just to sum up, Priyanka, the use cases seeing rapid adoption are the ones that involve high volume knowledge synthesis or complex creative generation or foundational discovery, where the alternative would have been very time consuming and an expensive human process.
Okay, that's great. And since we are doing a show on how to build an LLM based application, where does it not make sense to use an LLM?
Yeah, now given all the hype around generative AI, right, it's really, really important to have a decision framework for building a Gen AI application. And there really are three big questions here. The first is the one that you asked. Is it going to help or not, right? So we need to sort that out. And the second one is what's the right solution approach? And the third one is around model choices. But the very first one is the most important and critical one. Now, to understand why LLMs might not be the optimal choice for some applications, we need to first consider the relative strengths and weaknesses of these Gen AI models. So, if you think about it, these models come with built in world knowledge. They offer very powerful understanding and generation capabilities across unstructured modalities like text, images, and the downside, though, is that they can result in high latency and computation cost, and often they can hallucinate or lead to safety risks. So, for any application, we need to really evaluate what these models offer relative to the current baselines. Now, the benefits could be in the form of the improved time to solve, improved quality, reduction in cost, or new capabilities that were not possible before. Now, this evaluation is critical because if we don't do it, we might end up with poor choices. Now, broadly speaking, there are three groups of applications where GenA models turn out to be a poor fit when we do this evaluation of benefits. And let me call out these three groups. The first one is applications that do not involve understanding or generation over unstructured input like text and images. And obviously, because the model's forte is this unstructured input, so if we are not dealing with it, maybe we don't need them as much. And examples here include inventory optimization or structured predictive analytics based on tabular numeric data. Now, the second group includes high stakes applications which are centered around understanding but not generation of unstructured inputs. And this could be like fraud detection, medical diagnosis. Here we are still dealing with unstructured inputs, but we are only understanding. And the accuracy bar is really high. And usually for such tasks, we also have a lot of task specific label data. So it's better to train highly accurate and controllable encoder models that can be efficiently retrained as new data keeps coming in than go to generative models. Now, the third group includes real time, high volume, low latency systems like transaction scoring or e commerce product search ranking, where the computational costs and the inherent latency of generative models just makes them impractical for production use. Yeah. I mean, of course, I can go into more detail, but these are the three broad buckets.
If I were to summarize this, if you needed an application with a lot of accuracy and it has already been worked on with pre existing modeling and a solution exists, then don't go and use generative AI in these cases because it would not make sense. And also the fact that you might have some latency requirements that have to be met, which
Absolutely.
your current app does, then do not move to creating an LLM based app.
Absolutely. Yeah.
Let's move on to the next part of the show, which is we're going to talk about how we are going to choose a right model to build an LLM based application. And for this, I wanted to ask you the how based on an illustrative application. Suppose I'm building an e commerce app to buy tennis rackets, and the goal is to connect tennis buyers with the products they love, be it a racket or an accessory. How could a Gen AI based app help here?
Oh, yeah, that's a great example. So, when we are building an app, say in this case, to connect tennis buyers to products, or for that matter, any rich app, it's almost never a single task. Like I mentioned, the product search ranking, it's not like that. In reality, we will need multiple capabilities, and the GenA solve for each of these capabilities could be slightly different. So, let me clarify that with the example. So, here let's step back and think what needs to be built for this particular scenario. Essentially, we want to replicate a tennis store salesperson with this application. So, if we were to walk into a sports store to buy a new racket or shoes, the salesperson doesn't just give us a product. They start by understanding our needs. So, first, just by looking at us, they might make some implicit inferences about gender, whether we are left or right handed. And then they might ask some questions like what are we using, what issues do we have, and even probably see a short video of the swing. So, this first step is all about eliciting and understanding requirements. So, what we need here is a multimodal conversational interaction that allows text, image, and video inputs. So, here, beyond the plain knowledge that we might have, like plain world knowledge, we might also need some tennis expertise to understand what the customer is really saying and also ask the right questions to drill down. Now, once we are done with this stage, the salesperson would mentally shortlist a few products and come back to the customer, right? That is the retrieval stage. So in the digital version, the app needs to do this at a large scale, matching thousands of products to the user's needs. And often there's a vocabulary gap between the user language. The user might say a beginner racket, and the product spec might have something else like a graphite frame. And we need to bridge this gap. Now, this requires deep domain expertise on which products match which user profile. A salesperson would have built up this expertise over years. But in case of the application, we'll need to leverage historical transactions and customers' behavioral data, say what similar buyers have preferred in the past, right? And the way we do this is represent the customer's needs and the product specs in a shared semantic space, and then we do the match. Now, once we have done this retrieval, the user might have questions about the products that we are recommending, maybe the top 3 products we are recommending. They might want to know about discounts or their relative lengths or something like that. And that requires knowledge intensive generation, because we have to be really factual. We have to ground the responses in some real time data like the prices and discounts. So accuracy is paramount at this stage. Now, in addition to answering the customer's questions, we also need to present it properly. So the shopper might want to visualize the racket, or in case it's shoes, they might want to try that on. And there we might need some sort of multimodal generation capabilities, like, say, virtual try on. And it's not just the visual presentation, even the tone and language matter. So we might want to use the language that a salesperson would, like, say that this is an excellent choice or this fits your playstyle, because that really boosts the conversion. And this part is less about the knowledge aspect, but more about just creating friendly, emotionally intelligent language. And just to summarize, right? So the first stage was understanding the requirements, again in a multimodal fashion. Then there was retrieval. Then there was knowledge intensive generation and maybe reasoning. And then there was the presentation, which again could be multimodal and also involve persuasive language. So these are all the different capabilities. And I wanted to call these out separately because the Gen AI solve for each of these could be different. Yeah. So
Right.
once we know that these are the buckets, then we can drill down. And typically, what we need to do is break down the application into components or capabilities and then solve for each, because the baseline might be different for each, and the choices that you have in terms of models might be different for each. So you will benefit from having a modular solution.
Great. So these four big buckets have to be understood by anyone trying to build an LLM based application, which will then mean that you would get better results because you're making sure that these four buckets are taken care of. I think it's fascinating. It's really
Yeah.
good. I would have to go on to the next question, but before that, I should tell you the presentation is a very important aspect, as you said, because recently, 2 weeks back, I burnt about equivalent to $100 in Indian rupees because someone told me that the tennis shoe that I was buying would make me play like Roger Federer. So, yeah. Yeah, it's a very
Okay, so
similar thing.
that's a
So,
good app. I mean, from their perspective, I think that was a good sale. Of course,
yeah,
not necessarily the right thing, maybe
yeah.
for the customer, but yes.
That is great. So I think it would make sense to move on to the next question, which is I would like to know what kind of model metrics do I need to be aware of upfront to understand if my application is working correctly?
Okay. So, Priyanka, I was just wondering, would you like me to drill down into the solve for each of these before getting into the
Yeah,
model metrics?
yeah, that'll be good.
Let me do that. And then I think when we get to the metrics, it'll be like sort of clear, because I just called out the various capabilities or the classes of capabilities. The thing to remember is, like I said earlier, the solve for each is different, and it really depends on what you care about, right, for your particular application. And the factors that you need to consider are how quickly do you need the solution, how accurate you need to be, how much label data you have, whether you have the capacity to build ML models in terms of the team and the compute infra. And there are all these other considerations on the application setting like latency and throughput requirements. Is the content directly going to be sent to the users, or is it an offline process that where content sensitivity risks are lower? So these are considerations one needs to factor in, and based on that you have a different solve for each of these capabilities. And let me go over the four different task buckets I called out, right? Which were there's understanding, and then there's retrieval, both of which are discriminative, and then there is generation. So in generation we have knowledge intensive generation, and then there is generation which is based on world knowledge. No, I'm like setting aside the multimodality because the multimodality is an aspect that cuts through all of these four buckets. It's like applicable to all of them. So coming to understanding, this task is about interpreting unstructured inputs. We are not doing any generation, and this includes tasks like classification, entity recognition, object detection, segmentation, and so on. And here the output comes from some well defined closed set. And in this case, if your accuracy bar is on the lower side, you can quickly get good results by doing some smart prompting of foundation models. So even though it's understanding, you can use a generative model. Say you're doing a text classification, you can use a generative model if your accuracy bar is not so high. If the accuracy bar is high and you have lots of label data and you are well equipped to train ML models, then it's a good idea to fine tune encoder models though. Here you're not going to benefit from fine tuning generative models because that's expensive and you can't repeat it frequently. Encoder model is the right choice and it'll also be efficient. The next category that I mentioned is retrieval. Again, this is a discriminative task. And here we typically have a query and a repository of artifacts like products, images, and so on. And usually you have to rank these artifacts based on the match score. Now, when the scale is small, it's almost like understanding. But when the scale is large, then you can't use a very simple prompting based solution at all. Because if I have, let's say in this case that you mentioned, Priyanka, with the tennis products, if I have, say, 100,000 tennis products, there is no way I can fit in the description of all of those products in the prompt of a generative model. So, even when we want to do a prompting based solution, we start with some simple solution. Like, say, if you were to use Elasticsearch, you will have term frequency, inverse document frequency, TF-IDF, or BM25 based retrieval. You use that and then find a small set of matches, and then you take those and feed that into your generative model and get the top one. So you essentially re-rank them. That would be the first cut solution when you don't have a lot of label data, no ML capacity, and accuracy is not such a big deal. But for this retrieval problem, if accuracy is important and you do have label data, then again, the best thing to do is to go back to encoder models and really train them and then use that to find the best matching products. Now, there's a small subset of cases where generative AI models are useful, and that is the cases where we have a cold start situation where we don't have label data for some queries or for some new artifacts that have been added to our repository. For such cases, generative AI model helps, but typically the way we use it is we use them to generate synthetic data offline, and then we use that synthetic data along with the other label data to train the encoder models. So again, here we have a simple first cut solution and then a complex one. The simple first cut solution uses a weak retrieval and then a generative prompting based layer on top of that. The complex one just trains encoder models and then does matching. Yeah. So this was for the first two buckets. Now the third one is generation where we only need world knowledge, and tasks like summarization, persuasive copywriting, or some simple image edits would fall into this category. Now, most foundation models are trained very well. So the simplest and often the most effective thing to do is just smart prompting with these foundation models. And if we really want to optimize for latency, that is the only case when we might choose to fine tune our own custom models. Now, the fourth bucket that I called out was the knowledge intensive generation. And here we need deep domain knowledge because we need to ground this in facts and up to date information. And for this case, the foundation models won't work well because they might hallucinate or they might respond with outdated info. So, the first cut solution itself is RAG or retrieval augmented generation. So here the system would retrieve some relevant information from a database and then, feed just that relevant bit of information to the generative model, which will generate the final response. And again, as you get more proprietary data, you can, and you have more capacity to fine tune models, one can choose to fine tune domain specific solution. So just to summarize, for each of these four categories, right, we do have a simple solution which would involve prompting a generative model. But for the special buckets that we called out, like retrieval and knowledge intensive generation, we need to actually augment that generation with some retrieval. And the complex path is, of course, to fine tune our custom models, which could be encoder based models for the first two buckets, and it would be generative models for the second two ones. So I just wanted to mention this because people almost always just rush to generative models, but that's not necessarily the right solve most of the time.
Because it will not be accurate.
It might not be accurate, it might be more intensive. And it like ties back to your question, Priyanka, on when it would not be optimal, right? So these are like the variations of how we do the solve.
So now should we go on to the metrics that we...
Oh, yeah, definitely. So let me come back to the question on metrics, right? So like I called out, so we had to figure out whether it was good or not, like LLMs or generative models in general are good or not. Then the solve depending on the capability. And then we have to decide the right model. And to do that, the first thing you have to do is pick a set of candidate models that you really need to compare. And for that, you need to be clear on the input and output modalities of the task. So, what are we giving to the model and what do we want it to generate? Like, is text to text, or is this text plus images resulting in an image, and so on. Sometimes we might even have some specialized variations like code, gene sequence models. And we need to make sure that the candidate pool includes models for that specialized variants and also the general purpose copilots like ChatGPT, because these general purpose copilots now invoke specialized models under the hood. Now, once we have this set of candidate models, there are two broad sets of considerations. The first set is qualitative factors, and you should examine this upfront because that will narrow the choices, and it's like lower effort in general. And then come the quantitative one, which we validate through rigorous experiments. So the qualitative ones mostly deal with governance, legal, and operational factors. And these include deciding whether we want open access models where we can see and fine tune the parameters, or closed ones like GPT where we can only access through an API. So nowadays, some of the closed one or the black box models do allow us to fine tune, but that would require like sharing your own data on the cloud, and that might not be feasible. So this is an important consideration. Another consideration is whether the usage license fits the need. I mean, is sometimes we might just be looking to experiment or do research, but if it's a commercial product, then we need to be careful about this aspect. We also need to evaluate the liabilities for copyright infringement and whether our particular usage scenario is approved or not, like say retraining with the model output, because that's not permitted by a lot of models like ChatGPT and Claude. Now, in addition to these constraints, we also need to look at computation cost and throughput limits to see if they fit the application needs, because there might be an application latency and there might be an application budget. So these are all like things that we can do upfront. Now, when it comes to the quantitative evaluation, before we go to doing something specific on our own data, it's always a good idea to look at public leaderboards maintained by Hugging Face, Artificial Analysis AI, LM Arena, and so on, and look at the relevant benchmark so that we can narrow the candidate list. Because any experimentation is going to be costly, because we are like literally paying money for every invocation of these models, right? So you want to narrow down the list. Now, within the quantitative metrics, the most important ones are the ones that pertain to response quality. And these vary again based on the tasks or the capabilities that we talked about. In case of understanding or retrieval, we might track precision, recall, or ranking metrics. In case of just world knowledge based generation, we might look at fluency, realism of the images, or alignment with the instructions. In case of knowledge intensive generation, we would look at the regret rate, what fraction of questions it's unable to answer. We might also look at factual accuracy, completeness of the response, and so on. Now, for heavily regulated domains like healthcare, legal advice, in addition to these generic typical ML metrics, we should also look at metrics around out of scope detection. So we should not be answering things which are not within the scope of application, right? So for that, we need to detect it ahead of time. Whether we are leaking confidential data or PII data, that's an important metric. Safety of the content, compliance with guidelines, all of these need to be measured quantitatively on data sets. And this would ensure that, the model not only performs well, but actually behaves responsibly for our scope and context. Now, in addition to the response quality, we also need to assess the average latency, the average input context length, and output response length for our particular use case. And that's important because we need to be able to understand the cost benefit trade offs of all the models that we are evaluating. I just want to step back and say that, this quantitative evaluation with representative, unseen test data sets and well defined metrics, this is the core pillar of ML modeling. Yeah, right now I see a lot of folks who skip this step or do it in an ad hoc fashion, and it then comes back to bite you later because things won't work in production if we haven't done the proper evaluation. And in fact, I would say even before we build out a solution, it's always nice to lay down that success criteria in terms of hard metrics actually derived from the business needs and representative data sets that mimic the production setting. And we need to implement an automated evaluation mechanism. So in the beginning, the data sets might be very small, the metrics might not be complete, that's all fine. But as long as you set this up and you automate it, it'll make sure that you will keep doing this evaluation. And whenever there's a regression, you'll be able to track it. So what's happening right now is, the Gen AI models are actually evolving way more rapidly than our application needs. So new models are being released every so often. And if we have this evaluation framework set up, then as soon as a new model comes in, you can easily plug it in, compute the metrics, and swap out the models as required. So that's the right way to do this application building.
I think that's a very good point that you brought out, because if you set the ground success criteria, that will help you in also changing models as they keep appearing. Yeah, I think that's a very good rule of thumb, I think, that we should follow. Now I'd like to move into the LLM application architecture under the hood. The reason I want to talk about it is because we've fairly run out of time talking a lot about the model. I want to briefly ask you to lay down what are the typical components that one sees on LLM-based applications, mainly looking at the architecture over here. And can you also tell me which is the most important part, if that's possible?
Got it. Yeah. So far, we were like talking about metrics and the solution from an ML perspective, right? But when we really design these systems, you need to think about the software architecture of LLM applications. And the thing that's like working for a lot of people when it comes to building real large scale applications is this agentic approach. And most of the applications we build typically will not be the right fit for one big monolithic model, because you can't just have one model serving your text and images, so you can't control it as efficiently. So when you craft it well, it is a modular agentic system with multiple components, and together they take care of planning, execution, memory, reasoning, actions, and even reflection and learning over time. So, to understand what's going on, imagine a well run project team where each component maps to a specific role. So, at the top, we have the planner or the project head, and this is the person who understands the overall requirements and translates those requirements into a structured plan, breaking the work down into smaller, actionable tasks that the rest of the team can execute. Note that the planner doesn't actually do the work. The planner only defines what needs to be done and in what order. Now, this is where the orchestrator steps in. So, the orchestrator is like the program manager, the one who ensures that the plan actually gets executed by coordinating between the various members of the team, or in our case, the other components of the system. So, this orchestrator is not just a messenger, keeps an eye on the progress, and if something goes wrong, can go back to the planner and re-trigger the replanning. So together, the planner and orchestrator form the control loop of the system. So the planner designs the roadmap, and the orchestrator ensures that the journey stays on track. Now, supporting these two is memory. Think of this as, the project archive assistant who's responsible for maintaining the meeting note, all the decisions, task updates, so that everybody in the team has the right context. Now, without memory, the system might forget the context or repeat unnecessary work or repeat errors. But with memory, the agent can reason pretty coherently across sessions, or in case of chat, across various turns of conversation. Now, at the core of all of this planning and orchestration and memory, we actually have something even more important, which is the LLM itself. Think of this as the expert strategist, or like the Yoda of the team. This is the system's reasoning and thinking engine. And this is the one that interprets the goals, reflects on the past outcomes, and it provides intelligent guidance. So, this module doesn't actually execute anything, but it's the central intelligence that everyone else depends on for guidance. So this works behind the scene. Now, apart from all of these four core components, we also have a two layer which typically varies from application to application, and these are like the specialist members of the team. So the tools could be something like the programmers or the graphic designers, business analysts, and they do specific jobs which is assigned to them by the orchestrator. Now, in an automated system, these tools are APIs or external models, any kind of task specific components. Yeah, there are few special kinds of tools that are worth mentioning. The first one is a retriever tool. Sometimes people refer to it as a knowledge access tool, and this is equivalent to a research analyst who goes and fetches information, right? We already saw that retrieval augmented generation. That's RAG. There is a specialized retriever tool that goes and fetches information from databases or some external repositories, and that enables the agent to have access to factual information and, grounds it. The second one, which is again very important, is a safety or guardrails tools. Sometimes this is actually implemented across different layers as separate tools, but essentially it plays a role of a compliance or quality assurance officer. Make sure that the input is within scope and the output is safe and aligned to the policy guidelines, right? So that is the job of this tool. Now, just wanted to call out that, these tools don't just handle information, they can even perform actions. Like a tool could go and fill a form just like a human would do, send emails, control a mouse, or in case of embodied systems, it can capture images, stuff like that. So, putting it all together, the planner decides what needs to happen, the orchestrator manages how it happens, the LLM provides the intelligence, memory ensures that there is continuity of the context, and the tools do all the specialized work. And this process is also iterative, it's not like a linear flow. And planning, execution, reflection, learning, all of this happens in loops.
Mhm.
And there was this question that you had, Priyanka, on which is the most important. I would
Yeah.
say the planner orchestrator combination is really the control loop. And then, of course, the LLM itself, because that is really the intelligence that powers it all.
Right. And the tools give you the specific things that you require. So in our tennis case that we discussed earlier, you would have a specialist tool to give SME level recommendations that would be implemented in these tools, right?
Absolutely. So you might have a retrieval tool, you might have a specialized virtual try-on tool, which is the one that sold you
Mm.
Roger Federer's shoes. So you might have some things like that that are invoked by the orchestrator depending on the need.
I think this has been great because I think we've got a good overview of the architecture. The question I wanted to ask logically next would be, when you work with an LLM based app as developers or software engineers outside, sometimes we interact with one monolith. It's a black box. You just send a prompt and you get back a return. And then sometimes, as you say, you add a RAG. And then sometimes there's this agentic AI architecture where there's a master agent and a lot of, I don't know, slave agents which do the job. Could you talk a little bit about that? How does that fit into the architecture you just now talked about?
Right, right. And I'm glad you asked this because, I don't want folks to think that RAG architecture is something different from any of these, right? From the agentic one that we just talked about. So, what's happening here is if you look at a monolithic model, it is a team with one player. That one player is doing everything, right? Is doing the planning, orchestration, the LLM response, and there's no need for tools. So that's what's happening in case of a monolithic model. In case of RAG, you just have a very lean team with essentially three players. So because there is a single flow, there is no need for a plan or a planner. So we don't need a planner there. And what we have there is one tool, which is a retriever, which is going and fetching the relevant information. We have an extremely simplified orchestrator, which is just a messenger boy taking the retrieved information to the LLM, which is generating the response. So it is kind of like a simplified version of this architecture, which might make sense for some applications. I mean, if the application is simple enough that every invocation only requires a retrieval operation followed by generation, all you need is simple RAG system. But if you need something more complex, where depending on the user input or depending on the nature of the application, we need to make a dynamic plan, then you need a planner. And if you need a lot of different tools, like sometimes you want to answer a knowledge intensive question, sometimes you want to solve a math problem, sometimes you want to generate an image, then you would need a whole variety of tools and all of this additional coordination effort. Does that answer the query you had?
I think it does. Yeah. So thank you for that. And I also wanted to ask about validation, because oftentimes we would like the LLM system to behave properly and avoid offensive responses, copyright infringement, making things up. So, how important is validation in this architecture? Is that something that is going to be carried out by one of these specialist tools, or do we need to do something about that outside of the LLM based application?
Right. And so validation is definitely very, very important because these Gen AI systems are stochastic and unpredictable. So we really need a multi-layered defense. And like I called out, there would be some of these safety tools, right?
Mm-hmm.
Safety or compliance tools. And these are actually spread across different layers. So first you start with input validation, right? So this layer ensures that the user query or the context stays within the scope of the system. So if it was, an app for recommending tennis products, it should not be doing any medical diagnosis. Even if somebody were to ask a question, that's not its job. So the input layer needs to flag anything that is out of scope, unsafe, malicious upfront. And typically we use a mix of deterministic filters like whitelisted phrases, blacklisted phrases, regex patterns, and so on. And also some lightweight ML models. Lightweight because we don't want to add to the latency of generation, and also because they are more accurate at like flagging anything that is unsafe. And these checks have to be fast, right? So that's the reason we do this. And apart from the input layer, we also have some safeguards in the prompting layer. You can do that by giving instructions to the planner or the LLM core itself. And not just give instructions, we might also require it to sort of give feedback in the form of its own confidence. Apart from the main response, it can also give an output field which conveys how confident it is in this response, which can be a signal to the orchestrator, and the orchestrator can use that to decide if there is something else that needs to be done, maybe another round of verification or just blocking the response. Now, the next layer that comes into play is the output validation. So, in the output validation layer, again, we have similar to the input validation, we have a deterministic sublayer as well as a modeling based one. The deterministic one will have blacklisted phrases and so on. And the ML model layer could check for like things like bias, toxicity, factual accuracy, whether it's really entailed and grounded in evidence, and so on. Now, in addition to these input validation, prompting, and output validation layers, often we also have human in the loop mechanisms, like allowing the users to report problems with the output, and also a continual audit mechanism where, regardless of what's going on, there is a sample being directed to human auditors to review, right? And typically the nowadays the audit systems and workflows are also being semi automated by having LLMs assist the human auditors. So just to recap, you have all of these different layers, right? The input validation, prompting, output validation, and post response human in the loop systems. Maybe there's a tiny thing I want to mention, that in case people are wondering, do we still need deterministic layers in this validation? We do need it because those are the fastest ones to modify. Just in case something breaks, right? The quickest fix that you can do is go and, add a regex pattern or like some blacklisted phrases, and that will stop it from going viral and causing a lot of damage, and
Okay.
before we can retrain the models.
So do a lot of the validations also outside before you send it
Yeah,
to the
yeah,
model.
yes, definitely.
The next question to kind of wrap up this architecture section is to do with prompting. All of us have read about different prompting techniques like zero shot prompting, few shot, chain of thought, prompt chaining, chain of verification, including reading some tips about how we should keep the prompts designed in such a way that the most important part of the prompts are either in the beginning of the prompt or the end of the prompt. What is your take on this whole prompting, and is there something that we can do? Any tips that you can give us as listeners writing prompts?
Right, right. Yeah. The point that you mentioned on the placement is like really valid, right? There is a lot of research on positional placement and so on. And the key thing to remember is when we are trying to prompt, it's almost like you're giving instructions to a human, right? So it's important to make sure that the prompt is clear, well structured, and the more context and precision we give, the better the prompt performs, right? And typically a good prompt will have elements like the context, so that it can extrapolate if it needs to, clear input output formats, instructions which break down the task into simpler steps, input data, and examples. So these used to be the elements of a good prompt. Now, what has happened lately is that the models have gotten so good that we don't need to do all the hard work. Like, it is trying to figure out. So it internally there are mechanisms to take even not so great prompts and rewrite them before the model actually works on it. So that's happening with the current generation of models. So the onus on us has become a little like lower than before. You mentioned a bunch of these different techniques for prompting. So if you think about it, prompting really is like our language to talk to LLMs. So it's essentially programming through natural language. And most of what you called out, I can just briefly go over those prompting techniques. Like zero shot prompting is just a direct instruction. Few shot prompting is one where you give some examples. It's also called in context learning. So this is a case where we show a few examples and say, this is how I would like you to do the job. And for more complex reasoning, we use techniques like chain of thought prompting, and where we tell the model to think step by step and we provide examples. So this is similar to how one might do math problems. We would do step by step, and that reduces chance of error. Now, apart from that, there are a lot of other variants like self-consistency, tree of thought, graph of thought. And here the model explores multiple reasoning paths and it compares and picks the best one. Chain of verification is another useful one, where the prompt instructs the model to generate an answer and then double checks and critiques it. And when the tasks are, a little bit more complex, we often end up hitting context window limits. So in those cases, we actually break it down into multiple parts and use something called prompt chaining. So essentially, the output of one of the earlier prompts will be fed as the input to one of the later prompts. So if you think of all of these techniques, whether it is chain of thought, chain of verification, prompt chaining, or prompt decomposition, these are all very intuitive because that is how we typically solve problems as humans. Now, what I mentioned earlier, the earlier generation of these models, we really had to be very careful in terms of how we communicate with these models, I mean, how we prompt them. But now it's become much more easy. And the primary reason, like called out a little while back, is that a lot of these techniques have been incorporated into these models, and the focus actually has shifted towards automated prompt optimization. So automated prompt optimization essentially refers to methods that do away with the manual tweaking of prompts. See, in earlier days, people used to train models with labeled examples. So we would have, like, let's take a simple classification model. We would give a labeled examples, and then the model would look at the examples and learn the parameters. Now, what's happening with these foundation models is that they've kind of become like a black box to us. And the only thing that we can tweak is the prompt. So prompt has essentially become our parameter. And what folks have figured out is a way to automatically tweak the prompts based on a set of input and output examples. And some of you might know about gradient descent, right? So gradient descent is a learning algorithm where we take the old parameters, we look at the loss function on our label data, and based on that we update the parameters to give a new set. So similar to that, we now have techniques which are based on text gradients, where we look at the old prompt, we look at the loss or some metric on a given set of labeled examples, and then we update this prompt. Just said all of this is happening in the language space, and then we get a new prompt. Now, there are a bunch of tools out there. I particularly want to call out this framework called DSPY, and there's a nice software, not just like a package, but also a community around this. So, DSPY stands for Declarative Self Improving Language Programs. And here you can declare how you want your system to be, and it's not just a one model, but it could be a fairly complex agentic system. I mean, it could be even be a simple one, but it could also be a complex one. You can just declare the architecture of your system, and then it automatically writes the low level prompts and also optimizes them once you give it a bunch of label data. There's actually a lot of research going on in this space, but maybe we can get to it later if we have time. Yeah.
Yeah, probably have another show, but I will add the link to the GitHub repo, which is github.com Stanford NLP DSPY.
I think it's a great tool, and personally I've seen great results, so worth exploring.
We'll now move on to the last portion of the podcast. Well, I want to ask something about open challenges in the research area. I have read that in the future we would have multi-sensory models. Currently, we have our voice assisted apps like Alexa. But can you talk about any innovations that happen for the other sensory modes like smell or taste?
Yeah, you're right that we already have so many of these models that handle audio and visual inputs, but there is definitely a lot of fascinating progress happening in the space of multisensory models, and these integrate more of our human senses, and I would say even go beyond them. Meta's image bind is a prime example. Here they have a unified representation across 6 different data modalities. So that would be text, images and video, audio, touch and force, 3D depth, and even infrared thermal signals. And these are particularly useful for robotics and embodied AI systems. There are also breakthroughs in artificial smell. So, researchers call these electronic noses, and these systems use chemical sensors to detect organic compounds in the air, and they can pick up a lot of things that would be completely obvious for us, right? From detecting gas leaks, monitoring air quality, to analyzing human breath for signs of disease. So, there's a lot that can be done, and these are quite powerful. I want to also mention something interesting. There is this notion of Internet of Senses, iOS, but a different iOS. And here, the idea is that the AI model can serve as a cognitive hub or an artificial brain that can connect and interpret all of these sensory inputs: visual, audio, olfactory, haptic, and so on, and build a deep contextual understanding of the physical world. For instance, if you think of what we understand as an apple, it is, the visual input, how it looks, how it smells, the touch, all of that contribute to it. And what people are trying to do is, capture these signals through various sensors and reconstruct that conceptualization. Now, that is the understanding part. Now, the next step is to go beyond understanding and recreate an artificial apple or the sensation of an apple, right, for somebody else. And that's likely to lead to really rich, immersive, multi-sensory experiences. Now, one other thing to remember here is that as these AI systems begin to integrate sensors, which will capture signals across the sound and electromagnetic spectrum beyond the visible audible range, right? It will gain the ability to sense things that we can't, like things that are invisible, inaudible to us, things we might not be able to smell or taste. And that opens up extraordinary possibilities, which is to some extent scary, because they will be able to perceive the world at a level much beyond our own capacities.
Pretty scary. And I think that's something that we all have to watch out for, of what the world brings to us with all this innovation. I want to end the show by asking you a question. Every day, there seems to be a new innovation, a newer way of doing things. So, how to keep up with this fast pace of innovation?
Oh, yeah, that's so pertinent. And honestly, it is difficult for all of us. And, I do find the pace of innovation very dizzying because there's just so much happening. It's new tools, new models, new papers. It literally feels like you are at the receiving end of a fire hose. So I have my coping mechanisms, and I'm sure everybody does. So I could definitely share these. First thing I feel is we need to make peace with the fact that the old education paradigm where we study for a few years, school and college, and then coast through the rest of our career. So that one is gone. So we definitely have to be lifelong learners. And at the same time, we also need to accept that we cannot stay on top of everything. And, because the other thing is, if it might not be important to do that. The half life of knowledge has become so short that there actually is no point learning a lot of things that we are not going to use right away because it's anyway going to change. So, what seems to matter a lot more now is figuring out how to learn and adapt. And if you just look online, there's a lot of noise and very little good signal. And so, it's important for us to focus on number one, what do we really want to acquire in terms of knowledge, right? So it helps to curate some trustworthy sources, could be newsletters, could be people, authoritative people that you follow, or some forums that you participate in. So curation of sources is important. The second one is having a mechanism to sample what's going on. And this could be a periodic activity. In my case, just a few minutes a day, I just look through TLDR and some LinkedIn posts, and that gives me a sense of what new things are coming up. And even if I don't have the bandwidth to really deep dive there, I just kind of like bookmark it for later, and maybe once a week I go back to look at some of the interesting things. Now, apart from this, I do deep dive into topics that I'm really curious about or I'm going to work on soon. And one more thing that's important is there's a lot out there that's not being peer reviewed. So we really have to be critical in how we assess the information that's coming to us. There might be great ideas, there might be also flawed ideas, and it's important for us to have our thinking caps on. And in terms of tooling, Priyanka, I feel like tools like Notion, Notebook, LLM, they are pretty good. So those are things that we could use.
I think that's a good thing that you've given us in terms of what we could look at things a bit more critically and curate your knowledge sources. Thank you for coming on this show, Srujana, and giving us great insights.
Thanks so much, Priyanka. It was really nice chatting with you and enjoyed the discussion.
Where can people find you on cyberspace?
Just srujana@gmail.com. That's my email.
I'll add that to the show notes. Thank you once again.
Thanks, Priyanka.
This is Priyanka Raghavan for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.